Hello everyone, welcome you all at Lokesh Sir Unlimited Study Zone. So we are here with the chapter alternating current. Until in before this class, in our first lecture, we have completed the RMS value, the root mean square value of alternating current, and we got the relation that IRMS equals to I naught by root 2, that is equals to 0.707 I naught. It is equal to 70.7% of the peak value, maximum value. Okay. Now RMS value of alternating EMF. Okay, if you apply in the place of um current, you want to find the value of RMS value of alternating EMF means ERMS. So then you know by the Ohm's law, V equals to I into R. Okay, in a plain resistive circuit, V equals to I into R. So here ERMS equals to IRMS into R. Fine. ERMS equals to IRMS into R. Now, place the value of I naught here. IRMS today we find that equal to I naught by root 2. So this become I naught multiplied by R. By the formula I naught into R, it becomes maximum value of EMF. So ERMS equals to E naught by root 2. Clear? Because IRMS we have placed here I naught by root 2. So it becomes I naught into R becomes E naught. So it equals to E naught by root 2, that is equals to 0.707 of E naught or 70.7% of E naught. Fine. So this is the value of RMS value of alternating EMF. Got it? Okay. Our next concept is phasors. What are phasors? A phasor is a vector quantity. A phasor is a vector which rotate about the origin with angular speed omega. Okay. A phasor is a vector which rotate about the origin with angular speed omega. The vertical components of phasor are V and I, representing sinusoidally varying quantities V and I. So you see the vertical components of phasor V and I representing the sinusoidally varying quantities V and I. So try to understand what is phasor. Mm. Like voltage and current. Here I want to show you the phasors for voltage and current. Okay. So phasor means angle of phase phi equals to theta is equals to omega into t. This is the angle made by the phasor at any instant of time. Theta is equals to omega into t. Why? Because omega is equals to theta by t. Fine. So theta is equals to omega into t. Yes. So like this is a phasor. So at any instant t, the angle troubled by voltage or current is given by theta is equals to omega t. Clear? So check here. This is the phasor for current. Okay. So at any angle omega t1, here one quantity current I is shown. So till here, this is the magnitude of current I and this is the magnitude of voltage V. Clear? So the vertical component, vertical component, this will give the value. Vertical component of the phasor becomes V maximum sine omega t. Yes. The full length of the vector is equals to V maximum. So this will be the sine component. As you know, the vertical component will be the sine component. So this component, the amount of this component will give you Vm sine omega t. So check here the vertical component of this length. Okay. This length will give you V maximum sine omega t. Okay. Yes. This is the phasor diagram and this is wave diagram. Wave diagram. Okay. So you have a sinusoidal wave. This is the wave for voltage, sinusoidal wave for voltage, and another wave for current. The below one is the wave for current. Clear? Like there is at any instant t1, your angle is equals to omega t1. For any instant t1, your angle equals to omega t1. Clear or not? Yes. So at omega t1, your voltage will be given by, yes, this is the level of voltage because voltage axis will be there. So this is the level of voltage. So vertical component of the voltage is this much. Okay. And this component is equals to Vm sine omega t1. Okay, Vm sine omega t1. Now at the same place, the value of current is here. The value of current here. So at this place, the value of current equals to, this is for current. So the value of current is given by amplitude. This is the amount of current given by Im sine omega t1. Clear? So a phasor is a vector which rotates about the origin with angular speed omega. With angular speed omega, this vertical component of phasors V and I represent the sinusoidal varying quantities V and I. So the vertical component of the phasors, will represent the varying quantities. Okay, like V and I. Actually, more information about phasor means like there are two grounds, okay, in which a racing track was there. The racing track will be there. So if a particle move to start with a angular speed omega 1, and here the particle is moving with a speed omega 2, but if omega 1 is greater than omega 2, means this one having high angular speed and this one having low angular speed. Okay. So for a given time, like for t equals to 2 second, t equals to 2 second. Clear? So as the angular speed is here high, so the length traveled will be more. So this phase angle will be high and this phase angle will be lesser. Yes or no? Yes. So by the formula, omega is equals to theta upon t. Theta is equals to omega into t. So the angle will be here for t second. This will be equals to omega 1 t. And here it is equals to omega 2 t. Clear? Okay, so the angle moved is called angle of phase. This angle moved is called angle of phase. Clear? Hmm. And the vertical component of the phasor are called V and I. Okay, so these two diagrams are well connected, wave diagram and phase diagram. With the help of wave diagram, you can analyze the phasor diagram. Clear? Okay. So now student, we are moving towards the circuit response, our next topic. So we have to take the circuit response of different circuits. First, we are going to study right there topic AC circuit containing resistance only, or you can say it purely resistive circuit. So this is first one. So make the heading purely resistive circuit. Clear? A circuit that contains only resistance, no another component. So AC circuit containing resistance only. Yes. So let us source of alternating EMF that is connected to a pure resistance R. Okay, so there is a pure resistance. Across that you have connected an alternating supply, alternating EMF, source of EMF. Suppose the alternating EMF supplied is represented by E equals to E naught sin omega t. So this is the EMF voltage you have applied. You can also make the diagram like this. This is your resistance and this is your EMF supply that you have connected here. This is E. Okay. And alternating supply, the value of EMF at an instant equals to E naught sin omega t. Clear? Now, after when you connect in here the alternating supply. So there will be a time varying current IT will be there. Okay. So I equals to a small it. Time varying current we have considered is capital I. So let I be the current in the circuit at any instant t. At any instant t. Okay. So the potential difference developed across the R will be I into R because at any instant current will be fixed. So potential difference here developed V equals to I into R. By Ohm's law, V equals to I into R. Clear? Hmm. So the potential difference developed across the conductor, this sorry resistance equals to I into R. This must be equal to the EMF applied at the instant. As these two are parallel, yes or no? So potential difference across the this resistance will be equal to the EMF applied because in parallel voltages will be equal. Clear? So if the current I is flowing through here and resistance R is this, then the potential difference across the conductor will become equals to I into R. Okay. So I is the time varying current and R is the resistance. So you can write this IR as it is parallel with the battery. So this IR will be equal to E and equals to E naught sin omega t. Fine. So this I into R becomes equals to the E. So I into R equals to E means E naught sin omega t. Clear? Now I, the time varying current becomes E naught upon R sin omega t. Yes. This is what? This is I equals to E naught upon R. This will be equals to I naught, maximum value of the peak current. Okay, peak current. This is called peak current. So I equals to E naught upon R, maximum value of current. So the equation becomes here I equals to I naught sin omega t. Clear? I equals to I naught sin omega t. Yes. Hmm. So I becomes I equals to I naught sin omega t. This is the derivation for the alternating current in a series in a pure resistive circuit. The behavior of the R in DC and AC circuit is the same. R can reduce AC as well as DC equally effectively. By comparing equation 1 and 2, we can see that is an AC circuit containing R only. The voltage and current are in the same phase. Okay, yes. Now analyze these two equations. You have first your equation for EMF, applied EMF equals to E naught omega t. Okay. So first you have applied the EMF equals to E naught sin omega t. And after then you have find the equation for the alternating current I equals to I naught sin omega t. And this I naught equals to E naught by R sin omega t. Fine. This is equals to E naught by R. So you see actually what is happening here. This current reduces this amount because E naught sin omega t is fixed for both the equations. Here it is E naught sin omega t. Here it is also E naught sin omega t. But a new R term will be there. So it will decrease the amplitude of current. Yes or no? Okay. So a resistance only used to decrease the value of current. So, but check here. This curve for EMF follows the curve sin omega t. EMF follows the curve of sin omega t. Okay. And this I follows the curve. I जो है I follows the curve I naught sin omega t. The equation of E equals to E naught sin omega t, and the equation of I equals to I naught sin omega t. So they having no phase difference because this is also initially started with the same angular velocity from the same time. So they have traveled the same angle because omega into t equals to theta. So at time t, angle traveled by the first wave equals to theta. Similarly, the angle traveled by the second wave is also equal to theta. Clear? So they are supposed to be, they are said to be in same phase. Means during a purely resistive circuit, applied EMF and current are in same phase. Clear or not? They will be same phase, means angle of phase equals to 0. You can say phase difference equals to 0. Clear? Yes. So the voltage and current will be in same phase. So now make the phasor diagram. Phasor diagram. What is phasor diagram? A rotating vector that represents the quantity varying sinusoidally with time is called a phasor diagram. A rotating vector that represents a quantity varying sinusoidally is called a phase diagram. Look here, like you have a alternating current. Yes, the current is started from 0 degree and it's after 360 degree it completed one revolution. Yes or no? 2 pi. So here this current I, if I considering this amount of current, this is varying current I and its maximum value equals to I naught. Clear? So the current can change a value from starting from its 0 degree, here theta is equals to 0 degree, and time to time it will vary. Okay, so here theta after then completion of one complete angle, it is equals to 360 degree. Fine. So at any angle you can give the amplitude of current, you can give the amplitude of current. Like here, sorry, this diagram I have to make bit of above. Okay. So a rotating vector that represent a quantity uh, varying sinusoidally with respect to time is called a phasor. In phasor diagram, the peak values of alternating current I0 and the alternating EMF E0 are represented by arrows called phasors. Yes. So like this vector representing the current. So at the tip of the vector, you must write I0, means this is the maximum magnitude. Okay. This is the maximum magnitude. I naught is the maximum magnitude. Okay, so at the tip of the vector, you have to place there a sign I0 and maximum alternating EMF E0 are represented by the arrow called phasors. So these quantity are called phasors. Clear? They are inclined to horizontal axis at angle omega t and rotate in the anti-clockwise direction. The length of the arrow represent the maximum value of the quantity, that is I0 and E0. Okay. Now first try to analyze the wave diagram, then we will discuss the phasor diagram. So here two quantities are here. First we have applied E equals to E naught sine omega t, right? Means this wave, sine wave, follow the voltage equation for EMF equals to, this is maximum value E naught. Okay, and it's following the sine wave, so this is the wave for a sinusoidal EMF, right? Now what is I actually is equals to E naught by R, means you have divide the first one equation by some constant, so it becomes E naught by R sine omega t. So this will become E naught by R equals to I naught sine omega t. Clear or not? So by E naught divided by R, so the value of E naught divided by R, it will be reduces. So a new wave diagram for a current, alternating current will be like this. Yes or no? The magnitude of current will be less. Here the maximum value of current will be less compared to the E0. Why? Because I0 made from E0 by R. Clear? So by dividing it by R, it will have surely some less value. Clear, beta? Okay? Yes or no? Okay. Now, talking about the phasor diagram. Consider at any time t. Consider at any time t. Suppose this is your time t. Okay. Consider at any time t, check the values of current and voltage. This is the value of current and this is the value of voltage. Clear, beta? So this for at any time t, what is your angle? Angle will be equals to theta equals to omega t. Yes or no? Okay, so plot a value of current. Current is having less amplitude. So this phasor of current that having a maximum value of I naught with an angle omega t. So omega t is equals to angle traveled at t second. Clear? Okay. And also the E0 having more value, so its phasor will be long. So the maximum value of the current is given by E0. Clear? Now at that instant, like here at time t, instantaneous value is given by perpendicular component of this current. So this current having the perpendicular component, this one, okay, up to here. It is given by I naught sine omega t. At any instant of time t, it is equals to I naught sine omega t. Clear? Similarly, at time t, the voltage is given by the equation V equals to V naught sine omega t or E naught sine omega t. So the vertical component of this phasor for an angle omega t, this component becomes E naught sine omega t. Clear? So this will give you amount of EMF. Done? So see here, the phasors of voltage and current are having the same angles from the starting position. Omega t means what is phase difference between the both the voltage and current equals to 0. Clear? So the phase difference between voltage and current will be equals to 0. Okay. The projection of the arrow on the any axis will represent the instantaneous value of the quantity. Hmm. The projection of the arrow on any axis represent the instantaneous value of the quantity. The phasor difference between the two alternating quantities is represented by the angle between the two phasors E naught and I naught. So here we have the two phasors E naught and I naught, and as they are in same direction, so the phase angle will be equal to 0 here. Fine. In the AC circuit containing R only, current and voltage are in same phase. That is phase angle between alternating voltage and current through R is equals to 0. Fine. Student, you once again check the graphical situation. This is the value of V. So V is equals to, here it is given by Vm sin omega t. In the place of V naught, here it is taken Vm sin omega t. In the same phase, current is bit a low value. So I equals to I maximum following the sine wave sin omega t. Clear? So the phase diagram, phase angle will be equals to 0. Yes. Check here. Voltage, this is the peak value of voltage V naught. This is the peak value of current I naught. Okay. Yes. So this is the phasor diagram for the pure resistive circuit, and the phase angle between the voltage and current equal to 0. Voltage and current are in phase with each other. A phasor is a vector which rotates about the origin with angular speed omega. Done. So student, our next derivation is for AC circuit containing inductance only. Let a source of EMF is connected to a circuit containing a pure inductance L only. Suppose the alternating EMF supplied is given by E equals to E naught sin omega t. So what is happening here, beta? We have apply here we have apply a alternating source. So it will provide the changing current. Suppose this current equals to I, and you know by changing current the voltage developed across inductor, this is equals to VL, is given by L di by dt. Okay. So we have considered here I by capital notations. So the voltage developed here equals to VL equals to L di by dt. Fine. Yes. So negative sign only for change, sorry, the polarity change, or you can say opposition against the current. So if di by dt is the rate of change of current, through the inductor L at any instant, then the induced EMF in the inductor at the same instant will be, this is the amount of induced EMF equals to minus L di by dt. Fine. The negative sign indicates that induced EMF opposes the change of current. To maintain the flow of current in this circuit, applied voltage must be equal and opposite to the induced voltage. And in parallel, voltage cannot be changed. So the same amount of in parallel voltage will be same, means this induced EMF will be exactly equal to the applied EMF, right? So in parallel voltage will be same. So your the next line will be E0 sine omega t equals to L di by dt. Fine. So E0 sine omega t equals to L di by dt. This L di by dt equals to E0 sine omega t. Hmm. So L di upon dt equals to E naught sine omega t. Clear? Now di equals to, varying current di equals to E naught upon L sine omega t dt. Clear? So this di equals to E naught upon L sine omega t dt. Clear? By integrating both the side, so make an integration sign. So the integration will takes place like this. Integrating both the side, you must write here integrating both side. Integrating both sides. Okay. So after integration, di integration is equals to integration of E naught upon L sine omega t dt. Clear, beta? Now this becomes di. The integration of di becomes I, and E naught and L are constant. Clear? And there is a formula sine ax dx equals to minus cos ax upon a. So this is the formula for integration. So here for sine omega t, after integration you will have the integration of sine omega t equals to minus cos omega t divided by omega. Fine. So this is equals to E minus E naught cos omega t divided by omega L. Can you write like this? So here you have minus E naught omega minus E naught upon omega L cos omega t. Clear? Minus E naught upon omega L by the formula of class 10th, cos omega t cos theta equals to sine 90 minus theta. Fine. 90 means pi by 2 minus theta equals to cos theta. So you can replace cos omega t with the help of sine pi by 2 minus omega t. Okay. Yes or no? So cos omega t becomes sine of pi by 2 minus omega t. Take this minus sign inside here, dissolve it inside this, and this will become E naught upon omega L sine omega t minus pi by 2. This is your final equation for alternating current. Clear? Now one more thing. You see this E naught upon omega L. I am introducing a new term here that is called capacitive reactance. Inductive reactance, not capacitive reactance. So new term I am introducing here is inductive reactance. Okay, so our term is inductive reactance. As resistance, there is a resistance of a conductor means the property which opposes a flow of current is called resistance. Okay. During inductor, the opposition offered in the path of a inductor is called reactance. Like resistance, there in a resistive path is R. Here the resistance is given by XL. Okay. So this is called inductive reactance. Yes, this is called inductive reactance. Resistance is independent from the frequency of the current, but here the inductance is dependent on the frequency of the current. So it is working only on AC. So the value of XL equals to omega L. Remember, and the unit will be same. The unit of resistance equals to ohm. Here the value of, unit of reactance is also equals to ohm. Omega L ohm. Fine. Okay. So XL equal to omega L. So this is reactance. So in the derivation, you have to provide here omega L, E naught upon omega L. So in the place of E naught omega L, you can write XL. Okay, E naught upon XL. So I becomes I equals to E naught upon XL. So what is this? And sine omega t minus pi by 2. Clear? Now this E naught upon XL, in the at the time of current, we find that I naught equals to E naught upon resistance. This becomes the peak value of current. But this time there is a pure inductive circuit, and in a pure inductive circuit, there is a voltage, peak voltage E naught. When divided by the inductive reactance, it will again give you I naught. That is peak value of alternating current. So the term become I naught. Okay. So this is equals to E naught upon omega L, or supposed to be E naught upon XL. It is equals to what? I naught. Fine. So your final derivation will become I equals to I naught. This I equals to I naught sine omega t minus pi by 2. Clear? So your final derivation equals to I equals to I naught sine omega t minus pi by 2. So you have got your equations for alternating current or current response in an AC circuit. The time varying current here equals to I equals to I naught sine omega t minus pi by 2. Clear or not? Okay. So what is the difference here? E equals to the applied alternating EMF was equal to E naught sine omega t. We have applied an alternating EMF during this derivation. First, we have applied the source voltage equals to E naught sine omega t. And we found the amount of current produced here equals to I naught sine omega t minus pi by 2. Fine. So check these equations and try to analyze. Here, this is omega t. Okay, so let us draw the phases. So this is baseline, and with the baseline theta equal to 0. Okay, this is what? This is theta equal to 0. At time t, the angle for EMF equals to omega t. So this is the phasor for EMF, EMF E naught. Okay, and this angle equals to how much? Omega t. Clear? Now the phasor for the current here is lagging pi by 2 behind. Lagging pi by 2 behind means with respect to omega t, it is lag behind with an angle of pi by 2. So pi by 2 is called 90 degree. So here in the direction at an angle of 90 degree, yes, check. Is this angle looking like 90 degree? Yes or no? Yes, so it is omega t, and when you move clockwise, because positive angle means anti-clockwise, and this is negative angle will be taken in clockwise. So this whole angle becomes omega t minus pi by 2. Current will be there. Peak value of the current equals to I naught. Clear? So this is E naught, and this is equals to I naught. Clear? This is E naught and I naught. So this is your phasor diagram. Okay. Current having the value, instantaneous value equals to I naught sine omega t minus pi by 2, means current lagging behind the applied EMF by an angle of pi by 2. So who is leading here? Alternating voltage is leading here. Who is lagging here? Alternating current is lagging here. Clear? So current is lagging behind AC voltage, yeah, AC EMF by an angle pi by 2. Clear, beta? And what is phase angle between these two voltage and current? Angle of phase delta phi equals to pi by 2. Got it? Yes. So, so we find that in an AC circuit containing only L, purely L, alternating current lags behind the alternating voltage. Here current is in lagging position because current is running backward. Yes. Current having the phase pi by 2 radian less means in clockwise direction. You have to move pi by 2 angle. Okay. So current is lagging behind the applied AC voltage within phase angle of by a phase angle of 90 degree. So we can say 1/4 of a period. 1/4 of a period. Fine. Out of 360 degree, it is lag behind 190 degree. So it is called 1/4 of a period. Now draw the phasor diagram here. In the phasor diagram, AC circuit containing L, current lags behind the EMF by 90 degree. So the phasor representing I0 is turned clockwise. Remember, minus means clockwise angle through a 90 degree from the direction of E naught. So first take the direction of E naught. So this is the maximum EMF. Take the phasor of E naught. Okay. This component will give you what? The vertical component of E naught will give you E naught sine omega t. Clear? This angle in anti-clockwise direction you have turned omega t first. Clear? After then you have moved an angle of 90 degree clockwise. Okay, 90 degree clockwise. So you will have a phasor for current and the maximum value of current is equals to I naught. So the vertical component of this equals to I equals to this amount is equals to I equals to I naught sine omega t minus 90. Fine. I naught omega t minus 90. Clear? Hmm. So see, here current is lagging behind the voltage. Okay. Means E started with an angle of omega t. Means started at, see here, at t equal to 0. We have two relations. First for voltage E equals to E naught sine omega t. And for current equals to I equals to I naught sine omega t minus pi by 2. Clear or not clear? Okay. So current will become 0. Voltage will become 0. E equals to 0 at the time E naught sine omega t equals to 0. Okay. When E equals to 0, at a start point when E equals to 0, E naught sine omega t equal to 0 means sine omega t equal to 0. And sine theta equal to 0 when omega t equals to 0. Omega t is equals to theta. So theta equals to 0. Okay. So the phasor of alternating EMF will be started from theta equals to 0 because omega t equals to theta. So phasor from omega t will be started from 0. Fine. This is 0. This is pi. And this is 2 pi. Clear, beta? Now, I equals to I naught sine omega t minus pi by 2. Now, make the current, let find from where the current is started. So, I equals to 0. Take I equals to 0 means I naught sine omega t minus pi by 2 equal to 0 means take this sign at the denominator for 0. So, sine of omega t minus pi by 2 equal to 0. So omega t minus pi by 2 equal to 0 means omega t equals to pi by 2, or you can say theta is equals to pi by 2. As it is lagging, so it will start from theta is equals to pi by 2. So a diagram here, theta is equals to pi by 2. Check here. The your voltage is started from theta equal to 0, but your current will be started from theta equals to pi by 2. Fine. So your current will be started at an angle of pi by 2, so it will lag. So make a wave graph for current that will having some less magnitude comparative to the EMF, because this is E naught. So current EMF having the magnitude E naught, but current having the magnitude that is equals to I naught, and I naught becomes E naught upon XL. Fine. So it will having less value as compared to the applied EMF. Now, so this is started from pi by 2. So make a wave graph like this. So this is the wave graph for alternating current. Okay, pi by 2. You can also make it to here. Okay. Okay. So in this way, you have the graph for the alternating voltage and alternating current. Fine. Here omega L represent the effective resistance offered by the inductance L. Yes, I said you there is a effect omega L. Resistance also offered by the inductive coil, inductor coil, and this is omega L called inductive reactance. So XL equals to omega L. The value of omega is equals to 2 pi F. So moreover, you can write its value omega is equals to 2 pi F means frequency into L. 2 pi F L. Clear? Ohms. So omega L equals to 2 pi FL. F is called the frequency of the AC supply. Fine. Okay, talking about the DC circuit, if in the DC circuit, in the DC supply, F equal to 0, you know the frequency of the DC supply equals to 0. If you have applied an inductor across a DC, then what response will be there? Check here. A DC supply will applied across a inductor, pure inductor. Then this is a DC supply having voltage V. You know, DC supply having no fluctuation, no ripplings means frequency equals to 0. So what is offered resistance here? XL equals to 2 pi FL. If you place the value frequency equals to 0, 2 pi 0 into L, this becomes equals to 0. Means inductive reactance for a coil become 0. So there will be no resistance at all, and this path will behave as a ideal path, or you can say short path. Okay. And this circuit is supposed to be short circuit. Okay. So short path will be there. So in the AC circuit, F equal to 0, so XL equal to 0, so that a pure inductance offer a zero resistance to DC. Yes, it means a pure inductor cannot reduce DC. Okay, so a pure inductor cannot reduce, okay, or cannot limit the value of, okay, minimize the value of DC. Okay, it will pass whole the current through it. Okay, so a pure inductance offers zero resistance. It means a pure inductor cannot reduce DC. Now SI unit, the inductive reactance is ohm. The unit of inductive reactance is equals to ohm. XL equal to omega L. Okay. The unit of L, XL equals to omega L. Okay. XL equals to omega L. I am making the unit here for XL. XL equals to omega L. Omega is equals to 2 pi FL. Clear? Omega is equals to 2 pi FL. So F means hertz, L means Henry. Okay. F means hertz, L means Henry. Hertz equals to 1 upon second. So above it will be Henry, and below hertz is given by 1 upon second. Okay. Hertz can say it 1 upon second. So this becomes, sorry. It should be Henry. I said hertz here. Henry per unit second. Henry per unit second. So that is equals to volt per second per ampere per second. Okay. So this is the unit is equals to ohm. Obviously, It's a type of reactance, so its value having in ohm. Fine. Okay, moving towards the next circuit, students. Make a heading AC circuit containing capacitance only. So let a source of alternating EMF is connected to a capacitor only of capacitance C. Suppose the alternating EMF supplied is equals to E naught sin omega t. Okay, this is time varying EMF. You have applied across a capacitor. Let us suppose the current flowing in the circuit that transfer charge to the plate of the capacitor. This produces a potential difference between the plate of the capacitor. At any instant, suppose Q is the charge on capacitor. So the potential difference across the capacitor is equals to V equal to Q by C. Okay. So suppose some charge Q is transferred by this battery, by this EMF source. So at any time, actually this charge Q will be varying charge because this battery is time varying, so Q will be also varying. But any instant of time, suppose voltage across the capacitor equals to V. So V equals to given by Q upon C. Fine. V equals to Q by C. Now this voltage, this voltage equals to E voltage equals to E. As it is connected in parallel, at every point instant, this potential difference V must be equal to the EMF applied because this is connected in parallel. So the voltage across the capacitor will be equal to the applied EMF. Okay, so this Q upon C equals to E naught sine omega t. Clear, beta? Yes. Yes. One more method is there. Mhm. Like there is a capacitor and this is a time varying EMF. So suppose if current I is flowing through the capacitor, then what is current I? I is equals to, yes, what is current I? We know, so we got V equals to E. What is V equals to? V equals to Q upon C. So Q upon C is comparable with equals to compared with E naught sin omega t, that is applied voltage. So take Q. From Q we can derive the current. So Q equals to C E naught sin omega t. If I is the instantaneous value of the current in an instant t, then I equals to dq by dt. This is equals to d by dt. In the place of q, you put C E naught sin omega t. C and E naught are constant, so C E naught get outside. The differentiation of sin omega t, d by dt, sin omega t, it is equals to omega cos omega t. Yes, the coefficient of t will get outside. So it will be omega cos omega t. So put here omega cos omega t. Fine. Okay. Now omega cos omega t. So this becomes C omega and E naught cos omega t. Okay. So this can be written E naught C omega may be written as 1 upon omega c because it will again come if come to the numerator will give C omega and cos omega t. Fine. 1 upon omega c. Again 1 upon omega c is called inductive reactance. Yes. So 1 upon omega c is called, sorry, not inductive, it is called capacitive reactance. Capacitive reactance matlab resistance offered means resistance offered by a capacitor. Okay, resistance offered by a capacitor is measured in ohm. So in the place of 1 upon omega c, you must put here xc. So this will become I equals to E naught upon xc. Okay, I equals to E naught upon xc, and for maximum applied EMF, you will have the value equals to I naught. So this becomes I naught, this total becomes I naught, and this cos omega t may be written as sin omega t plus pi by 2. Sin omega t plus pi by 2 because sin 90 plus theta is equals to cos theta. So finally you have the derivation for I equals to I naught sin omega t plus pi by 2. Clear or not? So this is your derivation for current. I equals to I naught sine omega t plus pi by 2. Got it? Yes. So I equals to I naught sine omega t plus pi by 2. So here you see we have the equation for alternating EMF applied equals to E naught sine omega t, E naught sine omega t, and the value for current equals to sine omega t plus pi by 2, means in phase the current is pi by 2 advance than the applied EMF. Okay, means current is leading here and voltage is lagging. Means in an AC circuit containing capacitor only, alternating current I leads the alternating EMF by a phase angle of 90 degree. Got it? So here the current is leading the voltage by a phase angle of 90 degree. Clear? Okay, so phasor diagram. So we got the relation for alternating EMF applied equals to E naught sine omega t, and I we have found I equals to I naught sine omega t plus pi by 2. Clear? So this is zero phasor line, theta equal to 0. From theta at an omega t angle, this is at omega t, there is a phasor for voltage or EMF applied. Okay, but your current is in pi by 2 angle advance. Okay, so from here to at an angle of pi by 2. Yes. Okay, so here with an angle of pi by 2. So this complete angles become omega t plus pi by 2. Yes or no? Omega t till here and this pi by 2. So this complete angle omega t plus pi by 2, there will be a current called I naught. Okay, so this is the phasor diagram. Okay, check the phasor diagram. Yes, this is the phasor diagram. See here the EMF from the zero reference line, EMF having an angle omega t, and from this angle at a 90 degree, you have the value of current I naught. Okay, so the vertical component give the E naught sine omega t, and the vertical component of the current, maximum current, will give you the I naught sine omega t plus 90. Clear, beta? So the phasor diagram, I naught is turned anti-clockwise through an angle 90 degree from the direction of phasor E naught. Their projection on the y-axis give the instantaneous values of E and I. Okay, now the wave diagrams. So E equals to E naught sine omega t. Obviously, the sinusoidal wave from starting from t equal to 0 will like this. Okay, having the maximum value E naught is started at theta equal to 0 or omega t equals to 0 theta or omega t. Okay, this is 0. Now I for I naught I, we have the relation for current I equals to I naught sine omega t plus pi by 2. The time when I becomes equals to 0, this sine omega t plus pi by 2 equals to 0. So for current, starting point of current, I equals to 0, sine omega t plus pi by 2 equal to 0. So sine theta becomes 0 whenever theta equals to 0, means omega t plus pi by 2 equals to 0, means omega t equals to minus pi by 2, means theta is equals to minus pi by 2. Clear? So current is leading. That's why it's started before than your applied voltage. So this angle is equals to pi by 2, means 90, and here it will be minus pi by 2. So your current will be started from here. Okay. Yes, so phasor diagram will be like this. Clear? Okay, so your current will be started from here. So phasor diagram, check here the phasor diagram. Your current will be started from somewhere here at an angle minus pi by 2. So it will leading. Clear? So it will lead with an angle of pi by 2 for your alternating EMF. So this becomes the phase diagram, and this is becomes the wave diagram for both the voltage and current phases. Now, 1 upon omega c, we have talked about 1 upon omega c, that xc, that is capacitive reactance, xc equals to 1 upon omega c, unit of the 1 upon omega c becomes ohm. This is called capacitive reactance. If you place omega equals to 1 upon 2 pi f into c, okay. Check the response for DC circuit. For a DC supply, when you apply a capacitor, DC supply having the frequency f equal to 0. So XC for a DC circuit equals to 1 upon 2 pi into 0 into C. So this becomes 1 upon 0 and this is equals to infinite. Okay. So capacitor will offer infinite resistance. And when there is resistance equals to infinite means it behaves as a open circuit. Yes. You know, inductor behaves as a short circuit and this capacitor behave as a open circuit for any DC supply. Clear? So it will block the DC because no DC is permitted to go through this capacitor as the circuit is open circuited here. So it blocks the DC. So X equals to 1 upon 2 pi FC. In DC circuit, frequency becomes 0. So X equals to infinite. So a capacitor will block the DC. The unit of XC is ohm. Fine. Okay, so what we have seen from all the three circuits, just see a quick conclusion here. First, in the pure resistive circuit, you have seen the voltage and current are in same phase. Okay, voltage and current in same phase. Clear or not? For purely resistive circuit. Then purely inductive circuit, your voltage or your EMF is 90-degree leading. It means current is lagging behind 90-degree. Okay. So this was your current and voltage is leading. Fine. Then after in capacitive circuit, pure capacitive circuit, who will lead? Current will lead. Okay. By an angle pi by 2. So if your voltage is here, E naught, your current will lead with an angle of pi by 2. This will become your I naught. Clear? Okay. So note, R can reduce AC as well as DC because R having no frequency. So it will have only one function to reduce AC as well as DC. L cannot reduce DC. It can reduce only AC. Why? Because resistance of the inductor equals to XL. Yes. XL, resistance of the inductor for equal to XL. XL equals to 1 upon omega L. 1 upon omega L. Clear? So for high frequency, XL will be less. For high frequency, XL will be less. Means for AC of high frequency, generally AC circuits, AC supply having high frequency. So if omega will be high, your inductive, oh sorry, so sorry. There is a formula for XC. So XL equals to omega L, sorry. XL equals to omega L and XC equals to 1 upon omega C. So for high frequency, if omega will be more, your XL will be more. Clear? Means for high frequency AC, reactance will be high. So it will oppose for AC, but it will support for DC. Means it will reduce AC, but it will not reduce DC. So L cannot reduce DC, it can reduce AC only. Clear ki not clear? Because XL equals to omega L. So for AC, omega will be high, so XL will be high. Now, C block DC, but it allows AC to pass through. We have seen XC equal to 1 upon omega C. So if the frequency will be high, your reactance will be less. Means for AC, it will say resistance will be less, reactance will be less. It will be say, okay, go through. But for less frequency, for a DC, it will block and X equals to infinite. Clear? Hmm. So it will block DC but allows AC to pass through. through our alternating current in phase with the alternating voltage. Yes, we have seen the angle of phase equals to 0 degree there, delta phi equal to 0 degree. Through L, alternating current lags behind the voltage by a phase angle of 90, means voltage or EMF in condition of leading, but current in a condition of lagging. Through capacitor, alternating current leads the alternating voltage. Obviously, here the current will be leading and voltage will be in lagging position by a phase angle of 90 degree. Got it? So write the definition of next is susceptance. So reciprocal of a reactance is defined as susceptance. It is of two types. Inductive susceptance means susceptance for an inductor equals to 1 upon XL. And what is XL? XL equals to omega L. Fine. And susceptance of capacitor equals to SC equals to 1 upon XC. And you know 1 upon XC becomes omega C. Okay, so this is called capacitive susceptance. Clear? Okay, then a new quantity I am introducing here, this is called impedance. Okay, so when impedance will work, when you having at least two components, resistance and inductor. Okay, XL. So resistance and inductor, then the effective resistance is called impedance. So Z equals to given by Z. Impedance of the circuit is given by Z. Z equals to under root R square plus XL square. Clear? So Z equals to under root R square plus XL square. When the combination of resistance with a capacitor, so the impedance of the circuit is given by under root R square plus XC square. Clear? Hmm. So write impedance and then this is impedance. When you have at least two circuit element are connected together, then the resulting resistance of the circuit will be called impedance. Okay. Hmm. In the case of RLC series circuit, this is R, this is L, and this is C. So individual resistances are capacitive reactance is XC, inductive reactance is XL. That time Z is defined as under root R square plus XL minus XC whole square. Fine. This will be your impedance. So when at least two circuit components are connected together, then the resultant resistance will be called impedance. Clear? And admittance 1 upon impedance is called admittance. Only definition is important. So admittance equals to 1 upon Z. Clear? It is denoted by y equals to 1 by Z. Okay, so next topic, our make the heading AC circuit containing resistance, inductance, and capacitance in the series. This is called RLC circuit. So three circuit element will be connected together: resistance, inductance, and capacitance. So make a RLC circuit here. This first it is R, then L, then it is C. Okay. So connect the three circuit element RLC, R, L, and C. Three circuit element will connect it together and you will provide energize here with an alternating voltage or EMF, say V equals to V naught sine omega t. Okay. On action of alternating voltage, there will be a alternating current I will be there. Okay. So, so when I pass in through these three components, definitely there will be some drop voltage. VR is equals VR drop back on the resistance. VL will drop across the inductor and VC resistance will drop across the VC voltage will drop across the capacitor. Okay. So three voltage, individual three voltage VR, VL and VC will be dropped. Fine. Now VR. What is the value of VR? VR becomes I into R. As the current is I and resistance equals to R. So VR equals to IR. Now V, voltage across inductor becomes how much? I into XL. Fine. VL equals to current into resistance, but here the resistance becomes reactance, so it equals to IXL. And VC, the voltage across the capacitor becomes I into XC. Clear? Clear, beta? Now you know, in a pure resistance, in a resistance, the voltage and current are in same phase. In an inductor, the dropped voltage VL will be in leading condition with the flowing current, and here the current will be leading and the dropped voltage VC is lagging behind with an angle 90-degree. Fine. So here we have three situations. VC will lag, VR will be in the same phase. Okay. Three situations are there. Clear? Now make the diagram related to this phase diagram. Yes. So first take the initial point O. So first you take the voltage VR in this direction. Okay. In the direction, sorry, first you take the amount of current here. This is current, say I. So as the current is flowing, equal amount of current is flowing through the circuit and each element. Okay. So take a first current phasor. Consider the phasor for current equals to I naught. Clear, beta? So this is I naught. Now, you know the resistive voltage is in same phase with the current. So with an angle 0 degree in the direction of current, take this resist where voltage equals to VR. Okay, in the direction of current. Clear? Mm. Now, at an angle 90-degree from the current, because voltage is leading, so take the voltage VL here. I am showing it by blue color, sky color. Okay, this is your voltage VL. So it is having an angle 90-degree leading from the direction of current. So current is here and your voltage VL will be here. Fine. This is your VL. Then from the pink color, you know the voltage across the capacitor VC is lagging behind the current. So take a voltage VC here. Fine. The smaller voltage VC. Particular in this case, we suppose that VL is greater than VC. Okay. It may be reverse also, but in this case, in this case, we consider that VL greater than VC. Fine. Okay. So, so check here. We have the two phasors in a same line. VL is going upward and VC is going downward. VL having the magnitude this much and VC having the magnitude this much in opposite direction. Clear or not? If you reverse this voltage VC upside, it will become minus VC. Yes or no? So the resulting voltage will left out as VL minus VC. So let us suppose this is the reduced voltage and this is equals to VL minus VC. Fine. Yes, I have shown by this color, cream color, VL minus VC. Fine. Okay. So once again, first we have selected the basic phasor current I. VR is in the phase with resistive voltage. VL, that is 90-degree leading from the current, and VC, that is lagging behind 90-degree from the current. You just reverse the voltage, so it will become minus VC. It will reduce the amount of VL, and finally you have the voltage VL minus VC. Yes, this will be VL minus VC. Okay. So the resultant voltage is given by the magnitude of these two voltage. So complete a parallelogram and take the resultant of the two vectors. This is become the resultant voltage V. So by Pythagoras theorem, V square equals to VL minus VC square plus VR square. Clear or no? So V square equals to VL minus VC square plus VR square. Okay. So V equals to under root of VL minus VC square plus VR square. So this is the relation for resultant voltage. Clear? Hmm. Now, final angle of phase. You see the resultant voltage having a phase angle of phi. Okay, with the direction of current. So this is your resultant voltage and this is your current. So tan phi, finding angle of phase, tan phi is equals to perpendicular upon base. So perpendicular base, perpendicular becomes VL minus VC and base becomes VR. Check from the diagram. The perpendicular becomes VL minus VC. As it is VL minus VC, so this perpendicular also becomes VL minus VC and this base becomes VR. So VL minus VC upon VR. Clear? Tan phi you can take common. VL equals to I into XL. VC becomes I into XC. VR becomes I into R. Take I common from the numerator and denominator. And tan phi becomes XL minus XC upon R. This is called angle of phase. You can calculate phi. Just transmit this 10 on the right side and this will become your angle of phase XL minus XC upon R. Clear? Hmm. One more thing. This is equation number 1. So from first, okay. Rather than by first, you consider this one equation as first and this is second. So from first, V square equals to VL minus VC whole square plus VR square. Okay. So what is V? V equals to IR for purely resistive circuit. But here the total resistance become impedance. So you have to put here IZ. So IZ whole square equals to this becomes IXL. This becomes IXC whole square plus IR whole square. Clear or not clear? Take I square Z square. Now I square is common, so this will become XL minus XC whole square because I we have taken common. As effect of a square term will be outside here plus I square R square. Clear? I square into Z square equals to take I square common from all the or each and every term. Here it will be XL minus XC whole square plus R square. I square and I square cancel. So Z square equals to XL minus XC whole square plus R square. So Z equals to under root of make R square forward XL minus XC whole square. No, nothing. It is looking good. Okay. So take R square common because A plus B equal to B plus A. 3 plus 4 equal to 4 plus 3. So no worries. Okay. You can use as it is. Fine. So this become what? Impedance. Clear, students? Okay, so read the theory. So let RLC are connected in series to a source of alternating EMF. So the current at any instant through the three elements has same amplitude and same phase. That is equals to I naught sine omega t. This is varying, current from each of the circuit. As the circuit is from each of the element, as the circuit is in series, so each element having the same current, I, and I. Okay. This I equals to I naught sine omega t. But the voltage across the element has a different phase relationship with current. So maximum voltage across the R. Yes, maximum will be V maximum equal to I naught R. But voltage at any instant become equals to IR. Okay. So I have solved this derivation by using IR. Okay, yes, I have taken here check V R equals to IR, but maximum it will be V naught V R equals to I naught R. In figure, current phasors I naught represented along the OX. So this maximum value of current is represented. The current phasor, the I0 is represented along OX. As we are in phase with the current, so it is represented by the vector OA. Yes, so this is the amount of voltage VR. Okay, resistive voltage. The maximum voltage across the L equal to VL, that is equals to I naught XL, as the voltage across the inductor leads the current by 90 degrees. So it is represented by OB along OY 90 degree ahead from V naught. Yes, obviously this is the voltage VL. Okay, that is 90 degree ahead. Okay, and similarly, the maximum voltage across C, that is equals to VC equal to I naught XC, as the voltage across the capacitor lag behind the alternating current by 90 degrees. So it is represented by OC rotated clockwise through an angle 90 degree from the direction of current I naught. So OC is along OY dash. Where is OY dash? Yes, this is OY dash towards downward. Okay, as the voltage across the LNC have a phase difference of 180 degrees, so net voltage is VL minus VC, assuming VL is greater than VC. So in figure, it is represented by OB dash. So the resultant of the vector net EMF or net voltage, I have considered here net voltage V, but here it is given E naught equals to blah blah blah, all this thing. Okay, that's the total effective resistance of the RLC series circuit called impedance of the circuit. So corresponding to the maximum EF, you have the impedance equals to E naught upon I naught. Okay, V equals to RI. If you have applied voltage E, then E equals to RI. For a maximum EMF, you will have, sorry, it should be ZI. Z in the case of three circuit elements RLC. So E naught equal to Z into I naught. So Z becomes E naught upon I naught. Fine. So this is equals to E naught upon I naught equals to, if you bring this here, so this will be left as R is R square plus XL minus XC whole square. Now angle of phase, we find this tan phi equals to XL minus XC upon R. Clear? Final voltage may be given by the relation. What is the final voltage? If this voltage is V, so V is given by V equal to V naught sine. Yes, this is zero phase line, means omega t, plus the your final voltage making an angle phi. So it is equals to phi. So this will be your equation for voltage. V equal to V naught sine omega t plus phi. Clear? Look here. It is equals to E naught sine omega t plus phi. Done? So this is the derivation for RLC series circuit. Yes, better this diagram is, I think this derivation is better. For clear understanding, VR equal to IR, VL equals to IXL, VC equal to IXC. So VL taken upside, VC taken downside, the resultant voltage towards Y-axis equal to VL minus VC. Towards X-axis, it is equals to VR. You have taken the resultant, that becomes by the Pythagoras theorem, V square equal to VR square plus VL minus VC square. Okay, all the things are equals to like this. R equals to under root R square plus XL minus XC whole square. Okay, so here the calculation are done on the maximum values. Okay, but not required at all. You go through the original values. Okay, so refer this one sheet and do the derivation. Fine. Finally, you have the voltage V equals to V max sine omega t plus phi, because the final voltage have an angle of phi radian. Okay, done. Yes, so this is the value for angle of phase. Angle of phase we have calculated. Phi is equals to tan inverse XL minus XC upon R. Yes, see where is? Yeah, yes, phi equals to tan inverse XL minus XC upon R. So we also have calculated phi is equals to tan inverse XL minus XC upon R. Place the values of XL and XC. Tan inverse. What is XL? XL equals to omega L. What is XC? XC equals to 1 upon omega C divided by R. So this becomes final angle of phase. Okay. Equals to tan inverse omega L minus omega C up 1 upon omega C by r. Clear?